All right, let's jump right in. We're going to dive deep into the periodic table today, into a special neighborhood of elements that are, believe it or not, responsible for the color of our world, the power of our industries, and even the very breath in our lungs. We're talking about the unsung heroes of the D block, the transition metals. So let me start with a little riddle for you. What could your own blood, the catalytic converter in a car, and a handful of colorful gems possibly have in common? I mean, on the surface, they seem completely unrelated, right? But deep down, chemically, they all share one powerful secret. And that secret is they all rely on transition metals. Now, that official definition sounds pretty technical, I know, but it all comes down to this one little detail, an incompletely filled d orbital. Seriously, that's it. That one characteristic is the source of all their amazing properties. It's their chemical superpower, and it's what makes them so special. And what a list of superpowers it is. They can form these brilliantly colored compounds, they can change their charge, like a chameleon changes color, and that makes them incredible catalysts for, well, for pretty much everything. And what's wild is that all these properties are connected. So let's break down exactly how this all works. Okay, first up, let's talk about color. You know, from the deep blue of a sapphire to the rich red of a ruby, transition metals are basically nature's paintbrush. But how on earth do they do it? Let's look at a perfect example. On the left, we've got a solution of copper ions. Look at that beautiful, bright blue. And on the right, that's a solution of zinc ions. Totally colorless. Now, both of these are D-block metals sitting right next to each other on the periodic table. So why is one so vibrant and the other so, well, boring? The answer is hiding in those d orbitals. So here's the secret. When other molecules, which we call ligands, get close to a transition metal ion, they kind of mess with its d orbitals. They cause the 5d orbitals, which are normally all at the same energy level, to split into two different levels. You can think of it like creating a low-energy ground floor and a high-energy top floor. And this energy split is everything when it comes to color. See, when white light, which has all the colors of the rainbow in it, hits this ion, an electron from that ground floor can absorb just the right amount of energy to make a leap up to the top floor. It absorbs one specific color of light to make that jump. The rest of the colors, they just pass right through. And whatever light isn't absorbed is the color that we end up seeing. So if an ion absorbs orange light, it's going to look blue to our eyes. And this brings us right back to our copper and zinc mystery. Copper has an incomplete d orbital. There's an empty spot on that top floor, an open invitation for an electron to jump up. But look at zinc. Its d orbital is completely full, no vacancies. If there's no room for an electron to jump, then no light gets absorbed, and the solution is colorless. It all comes back to that one simple rule from the beginning. Now, let's move on to their next superpower, having variable oxidation states. Transition metals are the ultimate chemical shapeshifters. They can gain or lose different numbers of electrons with incredible ease, completely changing their identity in the process. And there is no better poster child for this than the element vanadium. I mean, just look at this. Depending on how many electrons it's lost, its oxidation state, it can be yellow, blue, green, or even purple. Each color is a completely distinct chemical, and it's just beautiful, direct evidence of these changes happening. And we can actually watch this transformation happen right before our eyes. If we take that yellow vanadium solution, that's the +5 state, and we add some zinc metal, we get to see this incredible cascade of colors. The zinc starts donating electrons, first turning the solution blue as vanadium gets reduced to the +4 state. Then it turns green as it hits +3, and finally it becomes this deep, rich purple as it reaches the +2 state. It's like a rainbow in a test tube. So, why does this happen? Well, the answer is in these numbers. They're called standard electrode potentials, and they basically measure how much a substance wants to gain or lose electrons. Think of a very negative number as someone who is really generous and wants to give away electrons. With a value of negative 0.76 volts, zinc is basically screaming, "Take my electrons!" while vanadium is more than happy to accept them. And this all boils down to a really simple rule in redox chemistry. A reaction will happen all by itself if the overall cell potential is positive. And because zinc is so eager to give up its electrons, it can basically force vanadium to take them, driving the reaction all the way from that yellow +5 state down to the purple +2 state. That's the chemical engine behind that amazing color change we just saw. Now, this ability to easily swap electrons back and forth leads us directly to what is maybe the most important application of transition metals, their job as catalysts. Think of them as chemical matchmakers. They speed up reactions that would otherwise take forever, making the impossible possible.
Now, catalysts basically come in two main flavors. You've got homogeneous, where the catalyst and the reactants are all mixed together in the same phase, like they're all liquids. And then you have heterogeneous, where the catalyst is in a different phase, like a solid piece of metal helping gas molecules react with each other.
And you can see the difference pretty clearly here. On the left, everything's all jumbled up together. But on the right, with the heterogeneous catalyst, that's where most of the industrial magic happens, right on the surface of that solid catalyst. And when I say magic, I mean world-changing magic. Two of the most incredible examples are the Haber process, which uses an iron catalyst to make fertilizer that literally feeds billions of people, and the catalytic converters in our cars, which use platinum and rhodium to turn toxic exhaust fumes into harmless gases. I mean, just look at the Haber process. It takes super unreactive nitrogen right out of the air we breathe, combines it with hydrogen, and uses an iron catalyst to force them together to make ammonia. Without this single process, modern agriculture just wouldn't exist as we know it. It's that important. And here's that little hero working inside your car's exhaust system. All the nasty stuff like carbon monoxide and nitrogen oxides go in one side, pass over that platinum and rhodium surface, and out the other side comes harmless carbon dioxide, nitrogen, and water. That's transition metal chemistry, cleaning our air every single day. So we've seen how these metals can build civilizations and clean our air, but maybe their most profound roles are the ones they play inside our own bodies and in the medicines that save our lives. Let's just look at two incredible life-saving examples. Hemoglobin, the molecule that carries oxygen in your blood every second of every day, it's a complex built around an iron ion. And cisplatin, a revolutionary anti-cancer drug, that's a complex built around a platinum ion. And the way cisplatin works is just pure chemical elegance. This flat, little platinum complex is the perfect shape to slide into a cancer cell's DNA. It latches on, creating a kink in the DNA strand. That kink makes it impossible for the cell to copy its DNA correctly, which means the cancer can't grow. It's just an amazing example of using the unique chemistry of transition metals to literally save lives. So from the brilliant blue of a copper solution to the chemical shape-shifting of vanadium, the industrial power of iron, and the life-saving precision of platinum, it's pretty clear that transition metals are absolutely the versatile, unsung heroes of the periodic table. All of their unique properties, every single one we've talked about, all stem from that one simple fact: having an incompletely filled d orbital. It has shaped our entire world, inside and out. It really makes you wonder, doesn't it? What other incredible secrets are still waiting for us to find, hiding right there in the D block? Thanks so much for joining me.